Welcome to Mathematical Structure for Computer Science. This is CS 113 at Pace University, also known as Discrete Mathematics. In these lectures, we're going to discuss about functions. This is our Unit 2 lecture number 3. So our main objective again is to go through what is a function, and we're going to study some few terminology, what is a domain, codomain, image, and preimage. Also, what is injection, surjection, bijection. Also, inverse function, function composition, graphing functions, floor, ceiling, and factorial, and also partial functions. So first, we start with the definition of a function. Here we say let A and B be non-empty set. So A and B are set with some elements. So a function f from A to B will be denoted as A implied to B. And here we say it's an assignment of each element of A to exactly one element of B. And we write f at A equal to B, again, if B is the unique element of the B set. The uppercase B is the set assigned by the function f to the element A of set A. So again, what this definition means is that always a function may have an input and output, or independent variable, independent variable. So let's assume that A is our input variable and B is our output. In college algebra, we may say a function f at x equal to y. X is the input variable, then y is our output. Now, in order to have a function, the input variable must generate only a unique output variable. So example here is if I have a student, let's say a student named Rodriguez. So here we have a function at student equal to grades. So the student will determine his grade based on how he prepared for the exams and he took the exams. So here, if Rodriguez student generate a grade of A, and all of the students generate only one unique output, or even two students can generate the same grade, then it's a function. But if we have Rodriguez that generates A and also generate B, then it's not a function. So normally in college algebra, we use a vertical line to check if a function, if a plot we have is a function. So for example, a function is given us, we are going to plot the graph of the function. Then we draw a vertical line through the function anywhere at any x value. Now, if the vertical line can touch 2 points on the function, then that means it's not a function. That means we can have one input x and it can generate 2 output. So our x will be the horizontal. I draw a vertical line, which means x is constant. I draw a vertical line, which means x is constant. But y can be any value. Now, if we have 2 values of y, the intersection on the graph, with only one x value, then it's not a function. So that's what we mean by this definition. Here we are trying to say that the set A element can only generate set B element uniquely. One element will generate, one set A element will generate one set B element, which is the output. So again, you have a function with a set A implies to B can also be defined as a subset of A by B. That's the relation of the elements. This subset is restricted to be a relation where no 2 elements of the same relation have the same element, the first element. So this is what we mean again. There's no way that we're going to have an input. Let's say here our input will be the element of A. There's no any element in set A that can generate 2 output that's two elements in set B, that means it's not a function. If an element in set A generates two or more elements in B, it's not a function. So a function means element in A will generate only one element in B. And this is the example from the diagram. So we have a element A, lowercase a, in a set uppercase A. Element B in a set uppercase B. So A will generate only B. And we say here the function is moving from A to B. Then here we have a function. So given a function f, A implies to B, we can say f maps to A to B, or f is mapping from A to B. A will be called the domain of the function. So our input will be the domain of the function, and the B is called the codomain of the function. In college algebra, sometimes the B also is called the range. So A will be the set of input variables. Then the B will be the range or the codomain. Then we can also say that B is called the image of A under F. So B is called the image of A under F. And A will be called again the pre-image of B. So A is called the pre-image of B, because A will generate the B. Then the range of the function is the set of all possible images of point A under the function. And we can denote that by F at A. So F at A, we start with the element. Any value we generate from F at A, B, C in the set A, element in set A, will be called again the range or the codomain. So here also we say two functions are equal when they have the same domain. And not only that, the same domain, but they also generate the same range or the same codomain. So two functions are equal when they have the same domain and the same codomain, and map each element of the domain to the same element of the codomain. So representing a function, here we say the function may be specified in different ways. It can be an explicit statement of the assignment, example, students and grade, example. Or we can have it as a formula, f at s equal to s plus 1. Or as a computer program. So function can be represented in three ways here. An explicit statement of the assignment, students and grade, example. Or a formula, f at s equal to s plus 1. Or a computer program, here we say a Java program that when given an integer n, we produce the nth Fibonacci. So our function name is a function that will give us the Fibonacci of a number. This will be covered again in chapter 5. So these are the three ways again we can represent function as an explicit statement of the assignment. This will be a sentences, for example, student and grade example, or a formula. This can be a mathematical formula, f at s equal to s plus 1. Or a computer program. Here we have a function Fibonacci to find a Fibonacci number. So here we have some few questions now. So far we went through the definition of a function. Again, a function always generates one unique output, one output. So if you have a function and there's input variable A, it shouldn't generate two output variables, then it's not a function. But rather it should generate one output variable. We may have two input variables that will generate the same output variable, that's fine. But the other way around is not. We cannot have one input variable to generate two different outputs. Then it's not a function. Then we also talk about what is a domain, what is a codomain of a function, the element. So let's see and answer some few questions here. The first question says f at a is equal to what? So I'll look at a, lowercase a, which is the element, and the arrow is pointing to z. So a will generate z output. So the answer will be z. The image of d is what? So the image of d, this is my d input. The image is also a z. It's pointing to z. Then the domain of the function is, remember the domain will be the possible input variable. So it will be a, b, c, d, which is, we can also represent as a set A. Set A consists of element A, B, C, D. So we can represent it as a lowercase a, b, c, d, all the elements, or we can represent it by A, uppercase A is set A. The codomain of the function is, it can either be set uppercase B, or also it can be X, Y, Z. The next is the pre-image of Y. So I'll go to Y and I'll see where the arrow is coming from. It's coming from B. So the pre-image of Y is lowercase b. Then F at A is the set. So F at A will generate what? Y and Z. Here, the reason why F at A is a set. So all the elements in the set is A, B, C, D. So we can see that A point to Z, B point to Y, C point to Z, D point to Z. So the answer will be Y, Z. Also, the pre-image S of Z is, so the pre-image of image or images of Z is or are, I would say are, because we have A, C, D. So the answer will be A, C, D. Also, we have questions on functions and sets. So here we say if we have a function, the input is A, and it generates the output B. And also S is a subset of A. Then F at S is the function F at S, where S belongs to set uppercase S. So the function ABC is, we can look at A, B, C, and that will give me YZ. The function CD will give me Z. So now we shall go through some few terminology. First, we start with the injection. We said the injection is a function F. A function F is said to be one-to-one or injective. So injection is one-to-one function. If and only if F at A equal to F at B, it implies that A equal to B for all A and B. So again, injection means every input will generate one output. So we have A, B, C, D. We can see that they generate Y. Sorry, they generate X, then Y, then Z, and W. So surjection will be onto. So a function F from A to B is called onto or surjected. If and only if again and only if for every element there is an element A that belongs to the set A, with F at A equal to B times A. So the diagram here can give us an example. Onto means we can see that all the output are already generated by the input. So we go to the previous diagram here, we can see that our second output does not again generate by the input A. Which is okay for injective, but for surjective or surjections, all the input must generate all the output. We also have bijections. So bijection, we say the function f is on one-to-one correspondence or a bijection. If it is both one-to-one and onto, which can be surjective and also injective. So yeah, they say we should show that f is one-to-one or onto. So this is the example here. They say let f be the function from a, b, c, d to 1, 2, 3 defined by f at a equal to 3, f at b equal to 2, f at c equal to 1, and f at d equal to 3. Now the question says, is f an onto function? So we want to know that all the input will generate all the output. There will be no any empty output. So our solution says yes. If the function is onto, since all the three elements of the codomain are images. So let's see the solution. Here, example said that let f be the function from a, b, c, d to 1, 2, 3. And we define it by f at a equal to 3, f at b equal to 2, f at c equal to 1, and f at d equal to 3. Now we say if this function is onto means again, every input will generate its own output. So the solution, he said yes. Why? Because f is onto since all the three elements of the codomain are images of the element in the domain. So if the codomain were changed to 1, 2, 3, 4, f will not be onto. So here we can see that our input is ABCD, but we can see that ABCD generate all the output 3, 2, and 1. And the output is 1, 2, 3. Now example 2 is the function f at s equal to s squared from the set of integer to the set of integer onto. The answer is no. Why? Because a set of integers is including negative value. So, but with the function f at s equal to s squared, even if s is negative, when we square it, it becomes positive. So this means it will not be on 1-to-1 or onto, because onto means every input will generate the output. We also have inverse functions. The inverse function, the whole concept is that we change the input to output, output to input. So if I have f at s equal to y, the inverse of f at s equal to y will be y raised to the power 1. I mean, f raised to the power -1, then at y. So the x will be substituted with y. And again, f will raise to the power -1, which represents the inverse of the function. So again, here we say let f be a bijection from A to B. Then inverse of f denoted by f to the power -1 is the function from B to A. Normally the function is A to B, so inverse will reverse it from B to A. So this is our inverse functions. So previously we have a to y, now it to be y to a, the arrow direction changes. Now we have a question here saying that let f be the function from a, b, c to 1, 2, 3, such that f at a equal to 2, f at b equal to 3, f at c equal to 1. Is f invertible? And if so, what is its inverse? So we want to know if the function is inverse. So what we're going to do is that we say the function is invertible because it is 1 to 1. The inverse function reverse the corresponding given by f. So the inverse of 1 is c, the inverse of 2 function is a, the inverse of 3 is b. So example 2, we have a f at x equal to x plus 1. If f is invertible, and if so, what is the inverse? So we have a function f at x equal to x plus 1. We want to find the inverse of it. So the function f is invertible because it is 1 to 1 corresponding. So the inverse, again, will not work here. And the function f is invertible because it is 1 to 1, x plus 1. So the inverse of this function will be f at y equal to y minus 1. We invert the positive to negative. F at x equal to x squared, this will be not invertible. As we said earlier, there will be negative values, but with this function x squared, the values will be positive always. So the function f at x equal to x squared is not invertible because it's not 1 to 1 function. We also have a composition function. A composition function is a function that is inside another function. So for example, if we have a function f and g, the composition function f at g at x squared, this means g at x is outside and it's inside the function of f at x. So anywhere we see s, we replace it with the function name. So we'll see an example soon. So for example, this stands for f composition g at x, or we can write it f g at x. And here we have a functions with elements a, then function b, and then c. So we can see that g go from a to b, then f is from a to c. When we combine as a composite, we may have from a to c now. So it will be f composite g. So here we have two functions, f at x equal to x squared, g at x equal to 2x plus 1. Now to find f g at s, or we say f composite g at s, it means I'm going to write down the function f at s. Then the variable x, anywhere I see x, I'm going to replace it with the second function, which in this case is again 2x plus 1. So here it's only x squared. So we replace x, we get 2x plus 1 by square, so we square it. Now if I'm going to find g f at x, first I'm going to write the g. Then anywhere I see x, I'm going to replace it with x squared. So we get 2x squared plus 1. So you have another example here saying, let G be the function from the set ABC to itself such that G at A equal to B, G at B equal to C, G at C equal to A. Now let F be the function from the set ABC to the set 1, 2, 3, such that F at A equal to 3, F at B equal to 2, F at C equal to 1. Now we say, what is the composition of F and G? And what is the composition of G and F? So first, let's try F and G. F and G will work because we know F and G means anywhere we see G, we are going to substitute F. Because it's F, G, so anywhere G. So in this case, we look at G at A. G at A is B. So we give that B to F at B, which is B. So the answer will be B. So F composite G at A equal to F, G at A, and it will be F at B, which is equal to 2. Because from the condition, we can see that F at B is equal to 2. So the next is F composite G at B. So G at B, that will give us F at C, because G at B is equal to C. And that will give us 3. But we cannot find G at F because of the composite, the subset. So another example, let F and G be a function from the set of integers to the set of integers defined by F at S equal to 2s plus 3, G at S is 3s plus 2. So here we have again, second example, F at S is 2s plus 3, G at S is 3s plus 2. So if I'm finding the composite of F, G at X, first I'll write down the F at X, which is 2s plus 3. Then I'll substitute G at S in X variable. So that's why we get here 2s plus 3 will give me 2 times 3s plus 2 plus 3. So again, F at S is 2s plus 3, G at S is 3s plus 2. So we get F composite G at X. Anywhere I see G at S, I'm going to substitute with X for F at X. So we get F at 3 plus 2. We have 2s plus 3. So S will be replaced by 3s plus 2. Because 3s plus 2 is G at S. We find the composite of it. Then we solve it. Then next we find G composite F at X. So we bring G out, we substitute F at X in anywhere we see the variable S in G at X. So we substitute the value here, we get 2s plus 3 plus 2, and then we get 6x plus 11. So graphing of a function, normally to graph a function, if it's a linear graph, we can find the x-intercept. X-intercept is the value of x when y is 0, and y-intercept the value of y when s is 0. So when you get the 2 points, then you can draw a straight line across it. But when you are doing non-linear, we need to set a table. So we have the input of x, the variable, and we can generate, from the function, we can generate the value of y. So we plot the points, then we draw a line across the point. So in a linear function, our variable exponent is 1. With this is a parabola, s squared. If then you're going to get a parabola. So these are some of the important functions. We have a floor function, which is denoted by the symbol here, and is the largest integer less than or equal to x. The ceiling function also, we have the symbol, is the smallest integer greater than or equal to x. So example would be 3.5. 3.5 ceiling, that will give me 4. 3.5 floor will give me 3. Now negative 1.5 ceiling will give me negative 1. So that's our floor and ceiling functions. And these are some of the useful properties of the floor and ceiling functions. So when we have the first, which said it means s is less than or equal to n and greater than n plus 1. Now, and then it's also the same, n minus 1. S is less than n minus 1 and less than or equal to s also. We can also prove the properties of a function. For example, prove that s is a real number, then we have this. If this, we want to prove this as a real number, we may have two cases. One case is if the decimal value is less than 0.5, then we ignore it. If the decimal value is greater than or equal to 0.5, then we approximate it to 1. And that's the step here. A factorial of a function, again, it's a function that we multiply. If we are looking for a factorial of 5, then it will be 5 times 4 times 3 times 2 times 1. So we say that a factorial of a function is denoted by f at n, lowercase n. N exclamation is the product of the first n positive integer when n is non-negative integer. So we may have f at a, factorial of, f at 1, the factorial of 1 is 1. Factorial of 2 to be 2. Then f at factorial of 6 will be 1 times 2 times 3 times 4 times 5 times 6. Factorial of 2 will give me 1 times 2. We also have what we call the partial functions. Here we say a partial function f from a set A to set B is an assignment to each element A in a subset of A called the domain of the function of a unique element B in B. So a set of A and B are called the domain and codomain of F respectively. Also, we can say that F is undefined for elements in A that are not, again, in the domain of a definition of B. So when the domain of a definition of F equals to A, we say that F is, again, total function. So this will be the conclusion of again, session 2.3. Again, here we are talking about functions, and our main goal is to go through the definition of a function, what is injection, surjection, and bijection. We also went through the inverse function. Inverse function, again, all we need to do is change the input variable to output, output to input, then sub the function. So again, I'm going to end here and wish everybody the best. Thank you.